Welcome, my dear friends, to the rapid roundup session on quantitative analysis for managerial applications. So in this session, we will be diving into the world of numbers, data, as well as decision making. So here we will be exploring how these quantitative methods can be used to solve real world problems which we would face as managers of various industries or sectors. This quantitative analysis is all about using mathematical and statistical techniques to understand, interpret, and make decisions based on data. So, whether you are in finance, marketing, operations, or any other field, the ability to analyze data effectively is very crucial for making informed decisions and driving success. Now, if you are new to this channel, I am Anu, your guide and facilitator for this course. I run this small but growing YouTube channel that is named Anu's Classroom. It is aimed at helping IGNOU students like yourself overcome the limitations of distance learning by providing you guys with quality content. So my goal here is to assist you in not only passing your exams with good grades, but also help you understand the concepts thoroughly so that you become better manager. So throughout this course, we will be covering a wide range of topics including descriptive statistics, probability, statistical inference, and decision analysis. As we go on with this course, you will find that a lot of things that we learn here were learned in our 9th and 10th maths and all. So this will also be a revision for those things. In case you have no background on commerce also, don't worry, commerce or engineering or any science related fields also, if you had maths, you would have studied this. If not, also we will look at it. And don't worry if you are not very good at numericals also, don't worry. If you study the theory also, you will pass. That is not an issue. The most important thing over here as managers for us is that we be able to analyze and interpret these things. Calculations can be done by any other department, but how, if we see a number, if we see a metric, what it means and what that figure means for us as managers, that idea is essential here, not your ability to solve any kind of problems, because there are a lot of tools available. We have calculators like that, we have a lot of tools available which can process your data and give you the results, but what the results mean, that you must know. So focus on that. So let us embark on this journey together, and I hope that this journey is going to be fruitful for the both of us. Now, let me provide you with a preview of what awaits us in this particular rapid roundup session. We will be covering all the 16 units in this MMPC 5. These 16 units are divided into 4 blocks. In the first block, we will lay the groundwork by exploring the basics of data collection as well as analysis. This is the very first step of quantitative analysis. We will speak about collection and presentation of data, the various measures of central tendency, variation, and skewness. Moving on to the second block, we will shift our focus to probability and probability distributors. Here we will brush up on the basic concepts of probability. Then we will talk in detail about discrete and continuous probability distributions and also on decision theory. Continuing into the third block, we will explore sampling and sampling distributions, including sampling methods, testing of hypotheses, and chi-square tests. In the fourth and final block, we will broaden our perspective on the various forecasting methods covering business forecasting, correlation, regression, and time series analysis. So let's get started. Now, before I start with the discussions, I kindly ask you to take a moment and ensure that you have subscribed to Anu's Classroom, and not just subscribe but also your notifications are enabled for Anu's Classroom, because by doing so, you can ensure that you will never miss an update from me, and in this way, you can fully utilize all the resources that I provide to support your journey towards earning your postgraduate degree from IGNOU. And when you come out with that degree, I'm hoping that you will also come out with not just a piece of degree, but rather knowledge on how you can manage your organizations better. Feel free to leave your comments, questions, or suggestions below. I'm here to help you out, so don't hesitate to ask anything. Just remember to keep your comments professional, like you would in your future managerial role. So, you know how when we are trying to figure stuff out and make smart choices, we always rely on having the right information. Correct? Whenever we go and buy a product online, we go and check the reviews. Why? What are those reviews giving us? Before we watch a movie, we go and check reviews. Before we even in Anu's Classroom also, before you decide on whether to spend the next 1 or 2 hours of your life on one of the videos that I have, you will go and check the comment section, right? So why do we do that? We are doing it to gather information, and that information is going to help us make smart choices, right? So what is it happening? This is data collection. So data collection is always the backbone of decision making. You can think of it as gathering up all the facts and figures that we will need to make informed calls. That means informed decisions. Whether it is businesses who are trying to understand what customers want, or governments trying to figure out how to help their citizens the best, or even individuals making big life choices like buying a house or picking a career, data collection is always the key. Even insignificant things also we right now collect data, right? Without data we cannot process. So it is all about getting the lowdown on what is going on, spotting any issues, and then making decisions that are armed with all that information we collect. So the data that we collect, we can classify it into two basic types. It could be primary or secondary. So primary data is the stuff that we collect ourselves. Like when we personally gather information through surveys or interviews and going and checking the review section in Amazon. That is primary data. Then secondary data is there. What is secondary data? Secondary data is that data which has already been compiled by somebody else. Like when we use the existing reports or databases, or we go and ask our friend to get to know what their opinion about a certain stuff is. That becomes secondary data. They will be saying from their own experience, but not from our experience, correct? So the primary way that we gather data, that is primary data, it is usually through questionnaires. You know questionnaires? Have you come across any questionnaires? If you want to know about questionnaires or how in detail, there is a playlist MMPP 001 that is for your third semester actually, but it is for project. So it doesn't, if you get time, you can go and check over there. I have given a sample questionnaire. Also, there are detailed notes on how you can prepare the questionnaire and all over there. You can go and check that out if you would want to know how questionnaires are made. Okay, it will come in handy definitely in your course. So questionnaires are like those handy forms that we use to ask people questions and get their responses. Another thing to consider with data is whether it covers the entire group that we are interested in or not. This entire group whom we are interested in is known as the population. And a portion of this population is called a sample. When it comes to gathering primary data, there are two main methods. One is observation, the other is questionnaire. So with the observation method, the investigator simply watches and records the phenomena being studied without directly asking any kind of questions. So this could involve humans who are doing the observing, or it could even be using machines or electronic devices. However, it can be tricky to ensure accuracy, especially if there are any physical limitations for the observer. On the other hand, the questionnaire method is more common because here the investigator can create questions and gather responses. This response gathering could either be happening face to face, or it could be by mail or over phone or Google Forms, whatever it is. It is thorough, but the thing is it can be time consuming as well as costly. When you think about a good questionnaire always starts with a cover letter that explains the study's purpose and assures confidentiality of the responses that are collected. A good questionnaire organizes questions logically. It includes cross-check questions for reliability. It keeps questions simple and clear and considers the number of questions based on the needs. Before we start using the questionnaire for our research, it is important that we pre-test the questionnaire to iron out any issues. Then, once we collect the data, we have to clean it up. That is, we have to make sure the data that we have is complete, it is consistent, accurate, and uniform. To make a questionnaire truly good to go, we have to ensure completeness. That is, every question should have an answer. And if something is missing, we have to try and fill it in. Either we will go and ask that person, or maybe sometimes if that is not possible, then somehow we'll have to try and fill it in without losing the credibility. So otherwise, it might be best to ditch that questionnaire. Like consider if there is no way that you can fill that response accurately, then maybe you will have to drop that response. Okay. So consistency is again another important aspect of a good questionnaire. We have to check for any conflicting answers and try to sort them out. Like for example, in one question they are asking, are you married? And you say yes. And in the next question they are asking, are you single? And you say yes. Married and single, can it happen together? Legally no, correct? So that means that particular respondent is lacking consistency. We'll have to remove it, or we have to either go back and check with them what is happening, or we'll have to think that that response never came in, like you have to discard that response. So that is consistency. Then accuracy should be there. We have to make sure that the numbers are spot on, and we have to watch for any outliers. Like for example, what is your age? If it comes -1 or if it comes 200, problematic, right? Are we dealing with a vampire or an unborn entity? We have to go and check again, right? So accuracy. Homogeneity. We have to keep everything uniform. From units of measurements to the terms used, consistency is again key for a solid questionnaire. When it comes to secondary data, we are basically referring to the information that has already been gathered by someone else. So there are two main types here, published as well as unpublished. Published sources are things like books, newspapers, journals, or government reports, which are basically anything that is out there for the public to access. On the flip side, unpublished sources are a bit more behind the scenes, like data from personal diaries or letters or reports that haven't been officially published. Secondary data can be super handy for all sorts of things, like adding extra information to our primary data, or giving context to research, or spotting potential issues, or forming hypotheses or testing them out, and even comparing with primary data. But there is a catch. That is, you have got to be careful. Secondary data can sometimes be a bit wonky also. There could be errors popping up due to things like biases, or very small sample sizes, or misunderstandings about definitions, or it could even be just the plain old mistakes in calculations. So before you dive in and start using the secondary data for your research purpose, it is crucial to double check that whatever secondary data that you have is the right one for whatever you are trying to do, and that is reliable enough for you and your needs. When secondary data is not available for the problem under study, then a decision may be taken to collect the primary data through original investigation. This original investigation may be obtained, or this original investigation may be carried out either by census, which is complete enumeration of everybody of the population, that is census, or sampling, that is you look at a small portion of the population, that is sampling. So with census, we try to collect data from every single item in the population, which will give us super accurate information. But again, it is a very big time and money commitment. Sometimes, like when we are testing materials, it is not practical to check every single item. So on the other hand, with the sampling method, we can take a sneak peek at the representative chunk of the population and make an educated guess about the whole based on that. This sampling method is a much more cheaper and quicker method than a full census. And if our sample represents the whole population, well, then our conclusions are again likely to be accurate. So we spoke about collecting data through different methods. Now let us discuss about how we can present the data, because how we present data is just as important as collecting it. When we organize, display, and summarize data effectively, it becomes much easier to make sense of the large amounts of information that we have with us. Clear and concise presentation helps us spot patterns, trends, as well as relationships within the data, which is valuable in fields like scientific research, business analysis, and public policy. So whether it is through charts, graphs, tables, or any other visual aids, a well-presented data set can make all the difference in understanding as well as interpreting insights. Classifying data serves multiple purposes that makes handling large data sets easier. First, it condenses vast amounts of data, making it easier to spot any key features. Secondly, it allows for comparisons between different attributes. Thirdly, it sets up data for presentation in tables. Lastly, it highlights the significant data features at a glance. There are various types of classifications, like geographical classification, which is based on an area or a particular region. Chronological classification is organized by the occurrence of events over time. Qualitative classification sorts data based on attributes. Quantitative classification arranges data based on magnitudes. So there are various classifications, and all these classifications help organize as well as analyze data effectively, catering to various needs and purposes. Constructing a frequency distribution or a discrete data involves listing all possible values of the variables in ascending order and then tallying the number of times each value occurs. These tally marks are commonly used for counting, with blocks of 5 marks and space between the blocks. The frequency columns shows how many tallies each class contains. For continuous data, we might have to choose suitable class intervals to create a continuous frequency distribution. And in this process, it becomes important to understand some key terms. A frequency distribution organizes data into groups or classes, with each class representing a range of values. The frequency is the number of observations in each class. When it comes to choosing class intervals, there are again some handy guidelines that we can keep in mind. Like, aim for a moderate number of classes, ideally between 5 and 15. This range is flexible, but smaller data sets lean towards fewer classes, whereas larger data sets would lean towards more. So keep the interval widths simple, like maybe 5, 10 or 25. Avoid all values like 3, 7 or 19 like that to the maximum, and try to make the intervals equal in width. However, for data within a very wide range, unequal intervals may be necessary, such as with income distribution. So start the first class at 0, 5, 10 or multiples of these, then it will become easier for you to calculate. For instance, if your data starts at 3 and your interval is 10, then the first class should be 0 to 10, not 3 to 13. Determine the interval based on the range of values and the desired number of classes. Like, for example, if you have income data that is ranging from 1100 to 5900 and we want 5 classes, then let us choose the interval of 1000. When tabulating continuous data, we can have two methods. Okay, we have two methods at our disposal. One is cumulative frequencies method and the other is relative frequencies. With cumulative frequency, we will add up the frequencies of each class interval, either starting from the lowest or the highest value. Each cumulative frequency will represent the total of all the previous class frequencies, including the current one. Like, for instance, in a salary distribution, we sum up the frequencies of all previous salary ranges to get the cumulative frequency for each range. On the flip side, we have the relative frequencies approach. Here, relative frequencies are proportions of the total number of observations that fall into each class interval. To find the relative frequency of a class interval, we can divide its frequency by the total number of observations. And this proportion will give us the relative frequency, and to express it as a percentage, we will have to multiply it by 100. Relative frequencies help compare different data sets and grasp probability concepts effectively. Once the frequency distribution is ready, it can then be presented visually using a bar diagram or a histogram or a frequency polygon or any kind of ogives. These graphical representations will help in visualizing the distribution of the data. A bar diagram represents frequencies with rectangles where the length of each bar will correspond to the frequency of a particular category. This is ideal for discrete data. Histograms are similar to bar diagrams, but it is used for continuous data with adjoining rectangles of varying widths. Frequency polygon connects the midpoints of the tops of the bars in a histogram with a line graph. So this becomes better suited for continuous data. Ogives or cumulative frequency curves displays the cumulative frequencies of each class interval in a line graph. There are two types of ogives. One is the less than ogive and the other one is more than ogive. To choose the right method, we have to consider the type of data that we are analyzing. Bar diagrams and histograms work well for discrete data, while frequency polygons and ogives are better suited for continuous data. If you want to know more about these data presentation or the various types of graphs, how we can make them and things like that, I have a detailed video about that. You can find it in the classroom in the playlists. I have a dedicated playlist for MMPC 5. So there you will find all these. So you can check it out according to your time availability. Measures of central tendency play a crucial role as statistical tools for summarizing and describing numerical data, aiming to find a singular value that encapsulates the essence of a very diverse data set. That is, if we have a very large data set and if I have to condense the information in that data set into a single value, then we have to use measures of central tendency. A very easy to relate measure of central tendency, I can say, is the gross domestic product, or you can even think about the average income or the income of an average Indian. We have people who are paupers to people who are world's richest men, right? World's richest people are also there in India. We have a very, very, very wide group, and each person will have a different income than the other. But if I have to say what is the income of an average Indian, so that I can compare it with the income of an average American and see if Indians are being paid less or Indians are paid more, then I have to condense all these incomes into one single value, right? So that is made possible through various measures of central tendency. Gross domestic product is also an example of this measure of central tendency. So commonly employed measures include mean, median and mode. each offering insights into the central position of a probability distribution. So, their significance lies in their ability to distill the extensive data sets into a singular value, thus facilitating comprehension and cross dataset comparisons. Like, for example, in comparing employee salaries between two companies, the mean salary provides a useful metric for assessing average compensation. These measures also assist in identifying outliers, extreme values that could skew interpretations. By detecting and considering outliers, analysts can make informed decisions about their impact on the overall analysis. To be effective, a measure of central tendency have to exhibit certain key characteristics, like it must be easy to understand it, and if it is easy to understand, then users can interpret the results with clarity. There should be a simplicity in computation so that we can have straightforward calculations. And the measure should consider all the observations in the data set, avoiding the exclusion of any data points. A clear and unique definition is also very necessary to prevent multiple interpretations of the same thing. Adaptability to further algebraic treatment is crucial for additional mathematical operations. Lastly, the measure should withstand the influence of extreme values or outliers, maintaining its representational integrity. In business and industry, a range of measures of central tendency are utilized to effectively summarize data, and these include the arithmetic mean, the weighted arithmetic mean, medians, quantiles, modes, geometric mean, and harmonic mean. The arithmetic mean is calculated by summing all the values and dividing by the total count, and it is widely used. Its counterpart, the weighted arithmetic mean, adjusts for the importance of each value. That is, against each data, we give a weight. Like, for example, when you are calculating your overall grades, your quarterly examination marks will be having less weightage. Your unit tests will have even lesser weightage. Maybe your half yearly and your annual exam marks have more weightage. So that is weighted means. So the other central tendency measure is the median. Median represents the middle value in a sorted data set. So it is particularly useful in the presence of outliers. Quantiles are again another measure of central tendency. Quantiles, like quartiles, divide the data equally. Like, for example, quartile, quart means 4, right? So a quartile will divide your data into 4 equal sets. Like that, there are multiple dectiles are there, which will divide your data into 10 parts. Like that, there are various quantiles. The mode identifies the most frequent value, offering insight into the central tendency. Additionally, we have the geometric mean and the harmonic mean also, which provides specialized perspectives. The relationship between these measures, that is the mean, median, and mode, varies with the data distribution. If it is a symmetrical distribution, then the if it is a symmetrical distribution, then the mean, median, and mode, all these three values will be equal. Whereas if it is a skewed distribution, then the mean will shift, leaving median and mode unaffected. Bimodal distributions may feature two modes, but again they maintain a single median or a single mean itself. Each measure has its strengths and weaknesses, influencing their selection based on data characteristics and analytical objectives. Choosing the appropriate measure always depends on factors such as the dataset's characteristics as well as our analytical goals. To compute various measures of central tendency like arithmetic mean or weighted arithmetic mean or median or mode or geometric mean and harmonic mean, all these things you can follow certain steps. Like, for example, if you want to calculate the arithmetic mean, simply sum up all the values in the data set and divide by the total number of values. If you want to calculate the weighted arithmetic mean, then we have to first multiply each value by its weight, and that multiplied value that you get, that you sum up and then divide it by the total sum of weights. Median, if you want to find the median, then first you have to arrange the values in either ascending order or descending order, better ascending order, and find the middle value. If there is an even number of values, then you take the average of the two middle ones. And if it is mode, if you want to find mode, identify the value that is occurring most frequently in your data set. That is mode. Geometric mean, to find the geometric mean, first multiply all the values together, then take the nth root of the product where n is the total number of values. If you want to find the harmonic mean, then reciprocate each value, 1 by each value, sum up the reciprocal, divide it by the total count, and then reciprocate the results again. Remember, each measure has its strengths and weaknesses, so choose the one that best suits your dataset and your analytical goal. Quantiles like quartiles, dectiles, percentiles, they all facilitate the division of a dataset into equal parts for analysis. Percentiles, you know, right? It will divide it, whatever data is there, it will divide it into 100 equal parts. So to graphically locate quantiles, we have to first draw a cumulative frequency curve and identify where it intersects with specific percentage points. For computation, If it is a quartile, we have to split the data into 4 equal segments. So Q1 will have 25% below and 75% above. Q2 will represent the median, that is 50% above and below. Q3 will have 75% below and 25% above. So there are formulas also for each of this. If it is dectiles or deciles, we divide the data into 10 equal parts. So D1 will have 10% below that point and 90% will be above that point, like that. Percentiles segment the data into 100 equal portions. And there are formulas for each of this. I am not going into detail on the formulas in this rapid roundup session. If you want to know about it, as I said, please go and check the detailed video. There I have explained everything. So these computations, they cater to grouped data, and different formulas apply for ungrouped data. Measuring variations are again crucial for understanding the spread of the data, assessing the average reliability of the data, comparing distributions, and conducting advanced statistical analysis. So it helps identify sources of variability, ensuring accurate interpretation and decision making in statistical studies. A good measure of variation should be easy to understand and calculate, catering to users of different statistical expertise levels. It must consider all dataset observations, providing a comprehensive representation of variability, and be robust to outliers, accurately reflecting the central spread of most data points. Comparability across data sets is again vital for meaningful comparisons, and the measure should be sensitive to changes also in the data spread. Compatibility with further statistical analysis is very much essential to ensure that the data is usable in advanced techniques. So well-known measures meeting these criteria include the range, the average mean deviation, the quartile deviation or the semi-interquartile range, standard deviation. You must have heard about standard deviation for sure, range also, right? So these measures are widely used for their effectiveness in capturing variability. Measures of variation serves as crucial tools in the statistical analysis, offering insights into the spread or dispersion of data within a data set. So these measures can be classified as either absolute or relative, each providing distinct perspectives on the variability. Absolute measures of variation such as range directly quantify the spread of data in terms of the original data points. For example, say the range of any data set, it is usually calculated as the difference between the largest and smallest values in a data set. Like for example, if you are a class of 10 people, then the range of marks of people in your classroom will be calculated as the lowest mark to highest mark, correct? So like that. So this range offers a very straightforward understanding of the extent of variability that is present. However, when you are comparing data sets that are expressed in different units, then we have to go for absolute. So these absolute measures may not be directly comparable. So to address this limitation, we go for relative measures of variation. These measures allow for the comparison of variability between data sets by normalizing the variation relative to a referenced value, often the mean. One widely used relative measure is the coefficient of variation. This expresses the standard deviation that is relative to the mean as a percentage. By standardizing variability relative to the mean, the coefficient of variation facilitates meaningful comparisons across datasets, regardless of their original units or scales. So in addition to the coefficient of variation, other measures of variation include quartile deviation, average deviation, and standard deviation. These absolute measures again offer insights into different aspects of data spread, complementing the information provided by the relative measures. So overall, both absolute and relative measures of variation play essential roles in statistical analysis, providing valuable insights into the spread of data and facilitating meaningful comparisons between data sets with differing characteristics. Skewness is a fundamental concept in statistics, indicating the asymmetry or the lack of symmetry in a distribution. A symmetrical distribution is evenly spread around its mean, median, and mode, whereas a skewed distribution displays an uneven spread. Understanding skewness provides valuable insights into the shape and characteristics of a distribution. The coefficient of skewness quantifies the asymmetry in a distribution, comparing its mean, median, and mode. To compute the coefficient of skewness, you can use the formula coefficient of skewness Sk is equal to 3 times mean minus median divided by the standard deviation. Alternatively, if the mode is determinable, then you can use coefficient of skewness as mean minus mode divided by standard deviation. That is also a formula. So a zero coefficient of skewness signals perfect symmetry, whereas if the coefficient of skewness is positive, then there is a right skew. If it is negative, then there is a left skew. Positive skewness suggests a longer right tail, and a negative skewness indicates a longer left tail. Skewness significantly impacts statistical analysis interpretation. In positively skewed distributions, the mean tends to surpass the median, potentially overestimating the central tendency. Conversely, if it is a negatively skewed distribution, then the mean would fall below the median, possibly underestimating the central tendency. So, acknowledging and addressing skewness is again essential for precise statistical inference. Relative skewness allows for the comparison of skewness between different distributions. By comparing the coefficient of skewness, analysts can determine which distribution exhibits greater skewness and also in which direction it exhibits that. So it is essential to remember that the coefficient of skewness is just one of the several measures that are used to assess the skewness, and it has to be interpreted alongside other measures for a comprehensive understanding of the distribution's characteristics. I know it could be a lot for you guys, especially right now, but I sincerely hope that you will take this MMPC 5 seriously, because it has a direct impact on how you understand MMPC 15 in your third semester, and MMPC 15 is a very crucial subject because it will help you do your project. As you all know, if you have taken MBA, if you have taken PGDM, then it is fine. If you are having postgraduate diploma, then okay, projects are not there for you. But if you have taken MBA, then project is there, and in order to do the project, you need to know all these things. So take this MMPC 5 seriously and study it very well, because it will help you in future as well. Even if you don't have projects also, take MMPC 5 quite seriously, because it will help you in your managerial role. That is one thing. But at least for projects' sake, at least you consider this important. So probability. Probability is not a new concept for us. We have learned about it from our school days onwards. Right? Remember anything? Okay, if you remember also, good. If you remember, very good. If you remember also, it is okay. So let us look at how probability theory can help us make decisions in uncertain situations, like even weather forecasting or stock market analysis. If you don't remember, don't worry. I'll try my best to give you an overview of probability in the coming chapters. Anyway, so probability theory. Probability theory offers a formal framework for quantifying uncertainty. Is anything certain in our lives? No. Right? But if we find out what is the probability that things could go right or things could go wrong, then it gives us a peace of mind, right? Yeah, so that is what probability theory does. It offers a formal framework for quantifying uncertainty, enabling us to assess the likelihood of various outcomes. So this allows us informed decision making based on probabilistic assessments by providing a unified approach to understanding uncertainty and offering various methods for measuring these probabilities. By calculating probabilities in various situations, we can make informed decisions and adjust our strategies based on the new information that we get. So in probability theory, the key concepts include experiments, sample spaces, and events. An experiment refers to any action that can yield a set of outcomes, like flipping a coin or launching a new product. The sample space encompasses all the possible outcomes of an experiment, with each outcome represented as a sample point. Like if it is a flipping of a coin, your sample space will be heads or tails. So events are subsets of these sample space, like a head falling is one event, a tail falling is another event. So events are subsets of our sample spaces, and they represent specific outcomes or combinations of outcomes. Like for example, if you are considering the coin toss experiment, as I said, the sample spaces heads and tails. Events could be the occurrence of heads or occurrence of tails. Similarly, if you are considering a market study, then the sample space might represent the potential demand levels for a product, and events would indicate the specific ranges of those demand. Understanding these fundamental concepts allow us to apply probability theory effectively in decision making across various domains, enhancing our ability to navigate the uncertain situations and make informed choices. To calculate probabilities in different situations, we need to first identify the experiment, the sample space, and the event. And once we have identified these, we can now use the appropriate approach to probability to calculate the probability of that event. Probability theory offers 3 distinct approaches to quantifying probabilities, each suited to different types of situations. We have the classical approach, we have the relative frequency approach, and we also have the subjectivist approach. The classical approach is applicable when outcomes are known to be equally likely. For instance, tossing of a fair coin. The probability of getting heads or tails is both half-half, 50-50. So here the probability of an event is defined as the number of favorable outcomes divided by the total number of outcomes. The relative frequency approach is employed when probabilities are not known prior. But we can observe the outcomes through repeated trials. Like for example, by tossing a coin multiple times, we can estimate the actual probability of getting heads or tails by observing the relative frequency of each outcome. So in this approach, the probability of an event is defined as the limit of its relative frequency. As the number of trials increases, what will happen? As the number of trials increases. So as the number of trials increases, the relative frequencies will change a little bit. So this is when we are actually tossing a normal coin, not a fair coin. Why? Because normal coins, they will have some manufacturing variations could tend to shift the weight a little bit here and there. It will not be fair always, right? So that is relative approach. The subjectivist approach is again utilized when facing uncertainty without any prior knowledge or data to estimate the probability. So here individuals will assess the probabilities based on personal experiences and the information that is available to us. So that is why this assessment is said to be very subjective, and it varies from person to person. In addition to these approaches, probability theories also provide essential rules for calculating probabilities in complex scenarios. These include the addition rule, the multiplication rule, and the conditional probability rule. By applying these rules alongside the appropriate approach to probability, we can effectively compute the probabilities in various situations, aiding decision-making processes. It could happen that we calculated our probabilities, we made our decisions, and now we have started implementation, and then later, once we started implementation, we are getting an additional information. It could happen, right? So when such an additional information becomes available, then we can also revise our probability estimates by using Bayes' theorem and see if we have to update our plans in any way or not. So Bayes' theorem is a theorem in probability theory which provides a way to revise our probability estimates as new informations become available. It states that if A and B are two mutually exclusive but collectively exhaustive events, and C is another event that is defined in the context of the same experiment, then given the values of probability of A, probability of B, and probability of C given A and C given B, the conditional probability of A given C can be calculated. To revise the probability estimate, we have to calculate the conditional probability event of A given the new information C. And this can be done using the formula probability of A given C is equal to probability of C given A times probability of A divided by probability of C, where probability of C is the probability of the new information. Probability of A is the prior probability of the event A, and probability of C given A is the conditional probability of the new information C given the event A. So by using this formula, we can update our probability estimate based on the new information. This method of Bayes' theorem, it can be used in various situations such as decision making, stock market analysis, and even weather forecasting, among a few to name. As future managers, we will certainly be handling uncertain situations in our job. That is for certain, right? Uncertain situations is certain in our jobs. So when we are faced with uncertainty, we often want to know how likely certain things are to happen, right? Suppose say somebody is admitted to a hospital and they need an operation. The outcome of the operation is definitely uncertain. It is mostly in God's hand, right? Even if a person is pregnant and they are going to deliver, the outcome is in God's hand. But we always ask the doctor, right, what is the chance? And the doctor will say a percentage, and based on that we will take a decision. So why do we do that? That is because we want to know how likely certain things are to happen. So that is where in such cases, so this is an extreme scenario, a hospital case, but I said it so that you will be much more, as if you are not already doing the job of a manager, then you will be able to easily relate to such examples. That is the only reason why I am saying like that. Okay, so even in businesses, these kind of situations often come up with, not the hospital case, but something similar. So this kind of situations is where random variables come in. So these random variables are like, you can say, mysterious quantities, okay, random variables, black box kind of thing, which can have different values depending upon what happens in an experiment. Now, to keep track of all those possibilities, we will have to have something called as a probability distribution. This probability distribution, simply put in layman's terms, I can say it is like a map. A map which tells us what outcomes are possible for a particular random variable and how likely each of those occurrences are. So when we talk about random variables with specific separate values, it is called as a discrete probability distribution. Such distributions are super crucial in statistics as well as decision making, especially when it comes to scenarios where outcomes are limited to specific possibilities. They basically tell us the likelihood of each possible outcome for a discrete random variable like integers or categories. There is also another type of random variable, one which takes on continuous values. These random variables are handled by the continuous probability distributions, but we will learn about continuous probability distributions later. First, let us focus on the discrete probability distributions. In discrete probability distribution, we need to know about the probability mass function, PMF. This probability mass function assigns a probability to each possible outcome of the discrete random variable. So it must satisfy two important conditions. That is, each probability must fall between 0 and 1, and the sum of all probabilities have to be equal to 1. Have you seen of any probability going beyond 1 or below 0? No. Each probability. So discrete random variable also have to have each probability between 0 and 1, and when you take the probability of the possible values of the random variable, all the possible values of the random variable, and if you sum it up, it should be equal to 1. Like for example, in a coin toss, heads and tails each have 0.5, and when you sum up, you get 1. A dice throw, each side falling will have a probability of 1 by 6. When you sum it up, you will get 1. So discrete probability distributions are lifesavers, I can say, in finance, in engineering, in healthcare, and many more areas. They are super handy when you're dealing with countable outcomes like tracking occurrences, successes or failures, or event frequencies. So you can think of them as the go-to tool for any kind of modeling scenarios, whether it may be predicting success in trials or events in intervals or the trials until the first success anyways. So why are we studying these probability distributions in the first place? Why are they so crucial? As I said, it is because they give us a roadmap for dealing with the uncertainty. And by looking at the probability distribution, we can figure out how likely different outcomes are and use that information to make smart decisions. Ultimately, all the things that we are learning in MBA course is all done in an attempt to make smarter decisions for our organizations. Think about it like checking the weather forecast before you decide whether to bring an umbrella with you or not. So it is all about weighing the odds and making the best choice. There are a few ways we can do this. One way is by using standard functions. Basically, if we know how things usually go in a particular situation, like in the case of flipping a coin or how many cars go by, then we can use these standard functions to figure out the chances of different outcomes. Think of it like using a set formula for common situations. Another way is by looking at the actual data. Sometimes we have already collected information on how often certain things happen. Now we can use this data to guess the chances of different outcomes in the future. So this is like making an educated guess based on what has happened before. And then there is the third way, which is more about using our own judgment. So if we don't have any data or formulas to rely on, we will just have to trust on our instincts and make our best guess about what might happen. This is definitely not a precise way, but definitely it is better than nothing. Something is better than nothing case here. So summary measures of a discrete probability distribution. These summary measures, they give us a quick idea of how a random variable will behave. So they are like shortcuts which summarize the whole distribution with just one number. Kind of like how we use averages in other situations, like how we saw about the central tendency measures. Now, one more important measure that we need to know when it comes to discrete probability distributions is the expected value. This expected value, you can say, is kind of like an average of the distribution. It will tell us what value we can expect the random variable to take on an average. That is the expected value. Then there is the median and the mode, which also will help us to understand where most of the values fall in the distribution. So again, summary measures are there like mean and variance and standard deviation and all. So these kind of summary measures, they offer valuable insights into the characteristics of our distribution. The mean represents the average value of the random variable. Variance and standard deviation quantify the spread or dispersion of the distribution around the mean. So these summary measures, definitely they aid in understanding the central tendency and variability of the random variable like variance or standard deviation. In particular, if you take these measures, the variance and the standard deviation, they tell us how spread out the values are in the distribution. They give us an idea of how much the values tend to differ from the average. Like, are they all closer to the average, or do we have very extreme outliers? All those kind of things we will get to know. so which in turn informs decision making. So overall, figuring out these probability distributions actually involves thinking about all the possible outcomes, figuring out how likely each one is, and making sure that all those probabilities add up to 100%, that is 1. By doing this, we can make better decisions when things are uncertain, and the summary measures will help us describe the distribution and understand the risk that is involved. By knowing more about how values are spread out, we can make better decisions, especially when things are uncertain. So when we spoke about discrete probability distributions, I also hinted about the continuous probability distributions, right? So let us turn our attention to that right now. Continuous probability distribution will handle the variables that can have infinite number of values, continuous random variables. So unlike discrete distributions which were dealing with separate outcomes, the continuous distributions will involve a range of possible values. So in continuous distributions, we will use a function. So in discrete it was probability mass function. Now in continuous we have a function, similar function, but it is called as the probability density function, PDF, to calculate the probability of that variable, whether it falls within a specific range or not. So this function, this probability density function, it helps us to understand the likelihood of outcomes in the real life scenarios where variables can vary continuously. The exponential and the normal distributions are the two important theoretical probability density functions which help us understand the uncertainty in various real life scenarios. The exponential distribution function, let us talk about that first. This is a very handy function for modeling the time-related uncertainties such as durations between machine breakdowns, or the length of telephone calls, or the lifespan of an electric bulb, things like that. So it is very super useful in situations where we are interested in the timing or the duration of events. Like for example, if our aunt is calling, what is the length of the phone call? Right? Or if our mom is calling, or if our dad is calling, we know it, right? How long this call is going to be. So like that. So in contrast, we have the normal distribution. This is incredibly versatile. It often shows up in diverse contexts. It is very great for describing the characteristics of products like their heights or weights or dimensions. Plus, it is commonly used in statistical analysis to approximate various continuous random variables. Continuous probability distributions are super handy when it comes to decision making also. Why? Because they let us gauge the probability of a variable that falls within a certain range, which is crucial when we are dealing with uncertain or variable data. Like for instance, they can help assess product quality or predict outcomes in various situations. The normal distribution in particular, it is the jack of all trades. It is used in a wide range of real life processes and statistical analysis. Overall, you can say continuous probability distributions are definitely powerful tools which helps managers like us make decisions that make sense of complex data and therefore make informed choices. So as managers, as I said earlier also, we often have to make decisions, or decision making is one of our primary job responsibilities. And when we have to take decisions, it is usually under situations where we do not know the exact outcome, right? Outcomes would be uncertain. So the art of decision making is something which we have to gather, which we have to perfect by the time our course is over. Decision theory can help you in that, because decision theory gives a structured way to tackle tough decisions, especially when we are faced with uncertainty, by helping us break down complex choices through identifying different options and the uncertain outcomes that are tied to each of those different options. Whether it is a one-time decision or it is a part of a larger series of decision making, decision theory has methods for each of these scenarios. And by mastering decision theory, we managers can make smarter choices based on logic and analysis rather than just gut feelings. It also lets us consider our own risk tolerance and preferences, making our decision-making process much more personalized. So first, let us look at sequential decisions. Sequential decision problems involve a series of decisions which are made over time, with each decision depending on the outcome of the previous decision. And to structure such decision problems that involve various alternatives and uncertainties in outcomes, we have something called as the decision tree approach. The decision tree approach involves creating a diagram which shows the different alternatives or the different courses of action that are available to us, as well as the possible outcomes that correspond to each action. So to create a decision tree, let us start with a square to represent the decision point or action. Okay, so first we will start with the square. So that is the decision point. And from this square, so it is like the root of the tree. We will draw lines, various lines, to represent the different alternatives or the various courses of action that are available. And for each alternative, we will draw a circle to represent the point of uncertainty. And then we will draw lines from this circle to represent the possible outcomes that correspond to each alternative. And for each of these outcomes, we will list the probability and the consequence of that outcome. And the resulting diagram will show the different alternatives and the possible outcomes and the probabilities and the consequences of each outcome. So if we have everything laid out as a diagram, definitely, rather than in our heads, because not everybody is very capable of having everything in their head and making decisions, right? Some of us, or let's say most of us, if it is all laid out in a piece of paper in front of us, it becomes much more easier to comprehend. So like this, drawing this and making such a graph can help you analyze the decision problem and choose the best course of action based on the expected value of each alternative. But again, it is very important to note that the decision tree approach is useful only for multi-stage decision problems. When it comes to single-stage problems, there is another method called as marginal analysis, which can be used much more efficiently than going for the decision tree approach. So marginal analysis is again another decision-making tool that is used to evaluate the potential benefits and costs of specific actions. So it involves examining whether ordering an additional unit or taking an additional action is actually worth it or not. In order to apply marginal analysis for solving decision problems that come under uncertainty, we have to follow certain steps. Let us look at it in brief. Yes. So the first step is you have to identify the different alternatives or courses of action that are available to us. We will determine the uncertain outcomes corresponding to each action. Next, we will calculate the expected marginal profit and the expected marginal loss for each alternative. Choosing the alternative with the highest expected value will be done once all these are done. That is the last step. So it is important to note that marginal analysis becomes helpful or comes helpful when we are solving single stage decision problems. If we have to take up sequential decisions, then we have to go for the decision tree approach. That will be more useful. Additionally, we have the expected profit or the expected monetary value EMV criteria that is also used in marginal analysis. It does not take into account the decision maker's attitude towards risk. Therefore, it is very important that we consider the decision maker's preferences and attitudes towards risk while applying the marginal analysis. It is up to us to do that. There is another theory which we also have to learn when it comes to decision theory. This is called preference theory. So preference theory is again a decision making tool which helps decision makers incorporate their preferences and attitudes towards risk into the decision making process. So this becomes particularly useful in decision making under uncertainty because it provides a systematic way of measuring the consequences of different alternatives on a preference scale that reflects the decision maker's attitude towards risk. In order to apply the preference theory in decision making under uncertainty, the decision maker have to elicit information on their certainly equivalence, that is CE, corresponding to each alternative. This CE of an alternative is the amount that decision maker is willing to exchange for the uncertain outcome of that alternatives. Once the CE for each alternative is determined, the decision maker can use these values to calculate the expected preference for each alternative. The alternative with the highest expected preference will then be chosen as the best course of action. Now, when probabilities of outcomes are not known, then what? All the while now we were discussing about the approaches where probability is known. What happens when probabilities of outcomes are not known? Then decision making can be really challenging, right? However, there are certain criteria that can be used to make decisions under such circumstances also. One such criteria that we have to know about is the criteria of pessimism. This criteria of pessimism involves assuming that the worst possible outcome will occur for each alternative, right? That is pessimism. What is optimism? The best possible outcome will occur. That's not going to help us make the smarter choices, right? When it comes generally, something might go wrong, right? So that is why we are going with the criteria of pessimism. What we will do? We will think about the worst case scenario in every alternative. And then we will choose the alternative which has the, the lesser of all the devils or all the evils, right? We'll choose that alternative which whose worst case scenario feels better than all the other worst case scenarios. That we will take, right? So what will happen then? We are maximizing the minimum payoff. So that is the criteria of pessimism. This is done when we do not know any probability. We do not know the probability of any outcome. Now it is important to note that there is no one size fits all approach. Okay, what I did for my specific scenario may not be what would be best for you in your scenario. So that is why I said there is no one size fits all approach. At least one thing that at least till now you are studying the 5th course in this particular semester, you should by now have got a generic idea that whatever we are studying are researches or the understandings of multiple people throughout the years, and everything, the underlying, the double line, the end result or the end observation that we make is that there is no one size fits all, right? What we are trying to do through this MBA course is expose ourselves to the various scenarios that a lot of other people faced throughout their careers, and have a basic understanding of what all issues they faced while they were inventing the wheel, so that when we face similar situations, we at least have a generic idea about what options we have in front of us, right? That is basically the purpose of MBA, I would say. So the best approach always for us will depend upon the specific decision problem that we have, as well as a decision maker, what are the preferences and attitudes that the decision maker is having towards risk. If I'm a personality who is averted to risk, I might do something totally different, or I might choose something totally different than you, who might have a different risk aversion. Maybe you are okay with risks, or maybe you like risks, so you will take something else. Maybe I'm not okay with risks, so I'll choose something else. So everything, finally, whatever choice we make depends upon the resources we have, our attitudes, our preferences, and our specific problem. No two problems are same. They may be similar but never the same. So earlier also we touched about sampling, right? When we were talking about population, we said about samples. So how do we take samples? Sampling is how you take samples. So sampling is like taking a sneak peek at a very big group to learn something about it without having to study every single member. So it is this sampling, it is a very handy trick that managers have used to measure characteristics of a large or even an endless group by studying just parts of it. So this sneak peek or sampling is pretty useful because it is way quicker and way cheaper than checking out every single thing in the whole group or the population. Plus, it often gives us pretty good results also, especially when the group is massive. Picking the right sampling method is crucial here. Then only our sample is going to be perfect, right? So picking the right sampling method is crucial, and it depends on what you are studying, the characteristics of the group that you are studying, and the resources that are available to you. So now let us explore some of the common methods of sampling. So have you ever put lotteries? Like, have you ever participated in lotteries? Right? Yeah. So imagine drawing names from a box. It is very fair, right? And it works for small as well as large groups. But it can be time consuming when it comes to huge populations, right? But that type of drawing names from a box kind of sampling is called as simple random sampling. Okay. Now, systematic sampling. Systematic sampling is picking every nth person from a line. Like, I have a roll book, so I will pick every 10th person. So first person I pick, then I'll pick the 10th person, then I pick the 20th person, then I'll pick the 30th person, 40th person, like that. Every nth sample. So if you are doing that, that is systematic sampling. It is efficient for large groups. Like if you have seen, in certain games, if the group is large, we'll say count from 1 to 5. If you want to make 5 groups, we'll say count 1 to 5. 1, 2, 3, 4, 5. Then again 1, 2, 3, 4, 5. All the ones in one group, all the twos in another group, all the threes, like that. That is systematic sampling. So it is very efficient for large groups. But if there is a pattern in how the population is arranged, like what if every fifth person is a girl, or every fifth animal is a monkey? If you're studying animals, your group 5 will end up with only monkeys, right? So if there is any pattern like that in your population, then systematic sampling is not your best friend. Then another type of sampling that we need to know is stratified sampling. So stratified sampling creates mini groups within big groups based on traits. And then we will pick one sample from each. Like for example, if I have 5 animals, then I will group all monkeys together, all the donkeys together, all the mice together, all the cats together. Now I will tell, okay, one monkey, one cat, one donkey, one mouse, like that. So that is stratified sampling. This ensures that there is a mix of people, but the thing is, we need to have a good knowledge of the population. We need to know how many, at least what are the distinct animals in your population. Only then I can do it, right? So that is one issue here in the stratified sampling. Then we have another type of sampling, that is cluster sampling. Cluster sampling splits the group into chunks and picks some chunks to study. Again, this is very useful if the population is very spread out, but again it needs representative clusters. Convenience sampling is very quick and easy. It is just like picking or grabbing whoever is nearby. Okay, I want to do a project work, I am going to do convenience sampling, so I'll just enter and I'll just go on the road, I'll just stand on it, whoever comes my way, I'll pick them. That is convenience sampling. I am not going to go and see how many elderly people are there, how many kids are there and all. Whoever is coming my way, I will take them. That is convenience sampling. So it is just like picking or grabbing whoever is nearby. But definitely it might not be representative. If there are very old people in your population, then they might not even be coming out and you will never get to know their point of view, right? So that is why convenience sampling will not be quite representative. Probability sampling ensures fairness, like drawing names from a hat. It is reliable, it helps reduce the bias, and it also lets us measure errors, making it very great for confident results. Non-probability sampling, it isn't as strict as probability sampling, but definitely it is simpler and it is handy for quick studies. It is quite practical, but it might not be as reliable as the probability sampling. While probability sampling method is seen as more reliable because it is fairer and it lets us measure errors, non-probability sampling is definitely, it is simpler. It can still give decent results in many cases. And sometimes probability sampling is not doable, like when the population is quite huge and we can't list every single member. So in those cases, we'll have to go with non-probability sampling steps. And non-probability samplings, in such cases, it will help us get a representative sample. Proportional stratified sampling matches the sample sizes to population sizes if the characteristics varies consistently across segments. Disproportional stratified sampling will adjust the sample sizes based on variations in characteristics across the segments. Multi-stage sampling will divide the population into smaller and similar subgroups, making sampling more efficient, whereas multi-phase, so this was multi-stage, now multi-phase sampling uses information from one phase to guide the next. This is useful when the population is not uniform. So both techniques improve accuracy and cost effectiveness, but they both require careful planning to ensure representative samples. When we are deciding on a sample size, we have to consider several factors. One major consideration is the variability within the population. If it is high, then we will likely need a larger sample. The confidence level is also crucial. Larger the sample, larger the confidence in the results, and this is often measured by the confidence level. Other factors could include cost. Larger samples can mean there is higher expense for data collection as well as analysis. Precision also matters, like how precise do you need your results to be. Population diversity is again another factor. Higher diversity means we will require a larger sample. Lastly, the chosen sampling method also can impact the size of samples. Carefully considering all these various factors that I mentioned right now is very much essential for determining the right sample size for our study. Sampling errors can significantly affect our study by distorting the representation of the larger population that we are studying. So here are some of the common sampling errors that we have to watch out for. We have to watch out for selection bias. Selection bias occurs when sample is not randomly selected, and this will lead to over or under representation of certain groups in the sample. Non-response bias happens when some individuals in the population don't participate in your survey or your study. That can also skew the results. Measurement bias arises when the data collection tool introduces its own biases, resulting in inaccurate results. Sampling frame errors occur when the list of potential sample members is incomplete or inaccurate, leading to a biased sample. Undercoverage bias happens when certain segments of the population are not included in the sampling frame, leading to incomplete representation. So being aware of these potential pitfalls and taking steps to mitigate them when designing your sampling plan is crucial for obtaining accurate as well as reliable results. Sampling distributions play a crucial role in statistical inference, providing the foundation for drawing conclusions about populations. Understanding the probability distribution of the sample statistics enables us to calculate the likelihood of a sample statistic that falls within a particular range. And this is essential for all the statistical inferences. Sampling distributions also facilitate the estimation of population parameters, hypothesis testing, and population comparisons, contributing to accurate statistical inferences and meaningful data interpretation. The sampling distribution of a sample statistic represents its probability distribution or probability density function. While every sample statistic has its own probability distribution, commonly used sampling statistics such as sample mean, variance, proportion, and median are particularly important for making inferences about populations. To observe the sampling distribution of the mean empirically, multiple random samples of a specific size are taken from a population and the sample mean is calculated for each sample. So, by examining the distribution of these sample means, we can gain an insight into the nature of the distribution. When the population distribution is normal, the sampling distribution of the mean will also be normal. However, the central limit theorem ensures that even if the population distribution is not normal with sufficiently large sample, typically greater than 30, the sampling distribution of the mean will approximate a normal distribution. Similarly, sampling distribution of the variance represents the probability distribution of a sample variance. This is observed empirically by calculating the sample variance for multiple random samples from a population. So when the population distribution is normal, again the sampling distribution of the variance will follow a chi-square distribution with n minus 1 degrees of freedom, where n is the sample size. Otherwise, the central limit theorem again allows us to approximate the sampling distribution of the variance with a chi-square distribution when the sample size is large enough. Then we have the student's t distribution. Student's t distribution is often referred to as simply the t distribution. It is utilized to estimate the population means when sample sizes are small or the population standard deviation is unknown. It differs from the standard normal distribution by being more wider and flatter, with the shape determined by the degrees of freedom. As the degrees of freedom increase, the t distribution will look more closely or will be more similar, or it converges towards the standard normal distribution with more degrees of freedom. Interval estimation is a statistical technique which provides a range of values within which the true value of a population parameter is expected to lie. And by specifying a confidence level, the interval estimation will quantify the confidence in the estimate. Confidence intervals for population means and population proportions are constructed using sample statistics, taking into account the desired confidence level and variability of the population. So, determining the sample size that is required for estimating population parameters will involve considerations like desired level of precision, the confidence level, and the population variability. Formulas for calculating the sample size based on these factors are available for estimating population mean and proportions and all, taking into account the z-score or the t-score corresponding to the desired confidence level or the desired margin of error. I am not going into detail on all those things because if I do, we will not be able to wind this session in at least this much amount of time, right? So, statistical hypothesis testing. This is like the detective work of statistics. This is very important also for your project. Okay, so MMPC 5 is important for MMPC 15 to make sense. Please be very attentive here, right? So statistical hypothesis testing, you can think of it like the detective work for statistics. It is all about making educated guesses or hypotheses about populations based on the evidence that we have from samples. So here is how we do it. First, we will formulate a null hypothesis. It is set as H0. Then we will also create an alternate hypothesis, that is H1. So null hypothesis is like default assumption. It will say that there is no significant difference or effect that is going on, like the default thing. Then the alternate hypothesis is definitely, it will be the opposite. It will suggest that there is something interesting happening in the population. So imagine we are testing a new drug for its effectiveness. Okay, so null hypothesis might be like the drug doesn't make any difference. Okay, this drug is useless. That will be the null hypothesis. While the alternate hypothesis will be that yes, it does, it works, it does make a difference. So that will be our null and alternate hypothesis. So we've got that. That is the first step. Next, we will choose a test statistic, uh, which is basically a number which summarizes our sample data. Okay, and then we will set a level of significance that is called alpha. This is like our tolerance for making a wrong decision. So usually it is set at 0.05 or 0.01. Okay, now we will define a critical region. This critical region is like our danger zone. So it is a range of values for our test statistic that would make us question our null hypothesis. And finally, we will compare our observed test statistic with the critical value. If our observed value falls in the critical region, then we will reject our null hypothesis in favor of the alternate. If it doesn't fall in the critical region, then we will stick with our null hypothesis. Oh, and don't forget about the significance level, okay? Significance level as well as the p-value. The significance level is how likely we are to reject the null hypothesis when it is actually true. That is, our tests showed that our observed values, observed values fell in the, it didn't fall in the critical region. So we rejected our null hypothesis in favor of our alternate hypothesis, but actually it was true, like our null hypothesis was true. So the significance level is shows that how likely we are to reject the null hypothesis when it is actually true. And the p-value tells the probability of seeing a test statistic as extreme as what we observed, assuming the null hypothesis is true. So if the p-value is small, it suggests that our results are pretty convincing. Now on to the tests themselves. We have got a lot of tests. We have got tests for population mean and population proportion, differences between means and differences between proportions, all these things. So for testing the population mean, we are basically asking if our sample mean is significantly different from what we think the population mean might be. Similar story is there for testing population proportions also. We are just looking at proportions instead of means. So we are basically asking if our sample proportion is significantly different from what we think as the population proportion. So when there are then there are tests for comparing two population means or two population proportions also. Like maybe we want to know if a new teaching method will lead to better test scores compared to the old method. So we want to compare two different data, right? Or perhaps we are curious to see if there is a difference in the customer satisfaction between two products, right? So these tests also, these comparison between populations kind of tests, they are super handy for making informed decisions, whether you are in business, you are in healthcare, or you are in social sciences, wherever you are working. And while you can do them by hand, there are mostly in organizations it is done via statistical softwares. Okay, so don't worry. Don't worry if you're not understanding how to calculate all these things. Don't worry, it's usually done via softwares. Like even when it comes to data analysis also, like in my day-to-day life, like I've used tools like Data Eco, I've used tools like Power BI. Lot of many tools are there from using which, like especially Data Eco, I've seen more of these things than Power BI in my domain. So yeah, these are the tools which we use. So don't worry, even if you are not able to do all these things by hand, don't worry. Focus on the theory, focus on understanding these concepts. And if you are not able to do it by hand, or if you are not able to memorize all those formulas, don't worry. That is not going to define your term and examination results or your career. Okay. Anyways, so they are definitely a key tool for drawing conclusions about populations based on samples. So you need to know how to read through these things, like read through as in understand what they are showing. That is crucial. That can be a that can be a deciding factor on how good a manager you are, or how good whether it is your own whether it is your own enterprise or somebody else's, how good you manage it, how good you can take it to success. That depends on your ability to understand the results from these things. So focus on that. So earlier we said about chi-square distribution, you remember, right? If you do, good. I think you're paying attention. If not, then rewind and check. Okay, I've said about this chi-square distribution. Now let us read about it. Let us try to understand about it. So this chi-square distribution is, again, it is like a Swiss Army knife of statistics. It is very super handy. It is super handy for testing if our data fits a specific distribution or not, checking independence between categories and much more things. Say we are checking if our data matches a certain distribution. Okay, so we will calculate this thing called as the chi-squared statistic. This chi-squared statistics measures how close our observed data is to what we would expect from a particular distribution. If the difference is small, then our data fits the distribution well, and if it is big, then the chosen distribution may not be a best fit for the data that we have. Now, if we are looking closely at the variance of a normal population, then we have got steps to follow. First, we will state our null and alternate hypothesis. Then we will choose our significance level, that is usually 0.5 or 0.01. Then we will grab a random sample and we will crunch some numbers. Our test statistic here will be the chi-square 1. And we will compare it to the critical value to see if our variance is different from what we expected. When we are comparing variances between two normal populations, then it is kind of like a face-off, right? We are checking if they are equal or if they are not equal. So the same deal as before, we create the null and alternate hypothesis. We will choose the significance level. Then we'll take the sample for data analysis. But this time we will use the ratio of our sample variances, and we will consult an F distribution table for the critical value. Okay. So goodness of fit testing is like playing matchmaker for our data and the theoretical distribution. So we are asking, do they vibe? Can we set them up? Can we set these two people up together, right? So we will set up our hypothesis. We will pick a significance level again. So we will grab a random sample and we will calculate our chi-squared statistic. And then we will see if it's got the chemistry with our critical value or not. Okay. So now let us talk about independence. So here we are looking at how two categorical variables are related. So we will start with our null and alternate hypothesis. We will choose a significance level, then we will collect some data, then we will whip up a contingency table, and then we will do the chi-square shuffle to see if there is a significant association between our variables. So all in all, chi-square distribution is very, very, very handy. That is what I want you to understand from this rapid roundup session. If you want to know in depth about this, please go and check the detailed video. Now, there are also other tests, okay, to test the independence. Like we have the Fisher's exact test, we have McNemar's test. So all these things are also there. They also come in handy when we are dealing with specific scenarios, like when our sample size is small or when our data is not paired up and things like that. But yes, chi-square distribution is very important for you to know. So business forecasting. What is forecasting? What is predicting? What is forecasting? Forecasting is like peering into a crystal ball. What crystal ball? The crystal ball for business. It will help us predict the future demand so that we can plan our moves accordingly. Forecasting. So by knowing what is coming, we can figure out the production, the inventory, and the distribution strategies, as well as make smart choices about pricing, marketing, and sales. Now there is a whole toolbox of forecasting methods out there. Some rely on gut feelings, while others they dive into the past data and whip up some complex mathematical models. Each method has its own pros and its own cons, and the trick to picking the right one, the trick here is to pick the ability of a manager to pick the right one for our job. So long story short, forecasting is vital for all sorts of planning decisions, from big picture stuff like expanding a plant or launching a new product to the nitty-gritty of daily production scheduling. Everything, forecasting is vital. So, and no matter the timeline, there is always a method out there to help businesses make informed decisions as well. Two of the most common forecasting methods are the moving averages method and the exponential smoothing method. The moving averages take the average of past data that is set over a period, and it will give more weight to the recent numbers. So it is similar to saying what's been happening lately is probably a good indicator of what will happen next. Meanwhile, the exponential smoothing does something which is quite similar, but it gives some extra love to the most recent data. Kind of similar only, that's why I told. So you can think of it like a fading memory. The further back it is, the less impact it has. Once the forecasts are made, it is not a set it and forget it deal. We need forecast control steps. So this forecast control helps to make sure that everything is on track. One way to do it is via control charts. So these control charts are quite handy when it comes to tracking the difference between the forecasted and the actual demand. As long as those differences stay within certain bounds, then it is all good. But if things start going haywire, then it is a sign that maybe it is time to rethink our forecasting game plan. So whether it is peering into the future or keeping tabs on the present, forecasting and forecast control are crucial tools in the business toolkit. They help businesses stay ahead of the game and make smart decisions to keep things running smoothly. You know, when you're trying to figure out how two things relate to each other, like maybe you're wondering if studying more would lead to higher grades, right? Or spending more money on ads could bring in more customers. So, well, that is where correlation comes in handy. Correlation is a way to measure how strongly and in what direction two things are connected. So you can picture it like this. You have got two variables, say x and y, and you are trying to see if there is a relationship between x and y. Like for example, you sleeping more, does it correlate to you getting less marks in your term and examination or not? Right? For example, or will watching only Anu's classroom videos help you pass in examinations or not possible? Right? So the correlation coefficient, which we will call as R. Okay, we are calling correlation coefficient. We denote it using the letter R, small r. It is a number which tells you just this thing. So it is a number which can range from -1 to +1. So if R is -1 or closer to that, it means that there is a perfect negative correlation. That is, if one thing goes up, then the other is bound to go down. If you sleep more, then definitely your time spent on any other activity is bound to go down. But if it is a +1, then that is perfect positive correlation. That is where both things will move in sync. Okay, like if you practice making chapatis more, then your rotis are bound to become more round, right? Something like that. Yeah. So and what happens if it is 0? If R is 0, then that means there is no correlation at all. Your ability to make perfectly round full rotis does not correlate your ability to build a rocket, right? R is 0. So to crunch the numbers and find out the correlation coefficient between two sets of data, you can use a formula which takes into account the average values of the variables and how each data point relates to those averages. Or if you are looking for a shortcut, then you can use a method which simplifies the calculations by assuming some average values. So it is all laid out in table 3 of unit 14's PDF document. So in unit 14, if you go to table 3, you will see all these various calculations there. Okay, you can go and check that. I am not going into detail over here. Anyways, now let us talk about testing, whether this correlation that you found is actually meaningful or not. So one way to do that is with a t-test. Students, t-test. Okay, so this helps you figure out if the correlation that you calculated is different enough from 0 to be considered real. Like for example, if you have got a correlation coefficient of 0.2 from a sample of 10 data points, then you will have to look up the critical t-value for a 5% level of significance with 8 degrees of freedom. And if the calculated t-value is less than or equal to the table value, then you will say that your coefficient is significantly different from 0. But what if you want to get a bit more specific and you want to find the confidence limit for your correlation coefficient? That is where things get interesting. Now you can use a chart like the one that is given in figure 3 of your unit 14 to plot out confidence bands that are based on your sample size and correlation coefficient. So for instance, if you have got a sample correlation coefficient of 0.8 from a sample of 10 and you find the 95% confidence interval by tracing along the chart until you hit the curves for your sample size, then it is like finding a treasure map for your correlation coefficient. Now let's switch gears and talk about rank correlation. Rank correlation is a fancy way of saying that we are looking at how two sets of rankings match up. It is handy in all sorts of situations, like when you are comparing rankings in food testing or rating contestants in a beauty contest. Spearman's rank correlation coefficient, which again we will also call as R, can help us figure out just how much agreement there is between these rankings. To calculate Spearman's rank correlation coefficient, you rank each observation in both sets of rankings, and then you will calculate the difference between those ranks, and after squaring those differences and adding them all up, you will plug everything into a formula to get your correlation coefficient. And if this correlation coefficient is close to 1, it means that there is strong agreement between the rankings, while a value near 0 means that there is no agreement at all. Now let us talk about why all of this matters. Correlation, is it just some math exercise? No. Correlation has got some real world applications, like real world applications. You can use it to forecast trends in your sales. You can analyze the data in factor analysis and group things together in classification and pick out important variables in regression analysis. Keep an eye on quality control, explore medical research findings, understand relationships in social sciences. So That is why I said it is really like a Swiss Army knife for understanding how things connect. Okay, wait, it's not over yet. I know you're bored, but wait, there is more to this. So, have you ever heard of autocorrelation? It is a correlation only, but it is for a variable and its past values over time. So, autocorrelation is how the same thing correlates with the past, like how different or how similar is the present me compared to the past me, right? So autocorrelation helps you spot patterns in time series data like trends or seasonality or random ups and downs. You can plot it out to see if there is a repeating pattern like a yearly cycle or a weekly trend. To calculate autocorrelation, you have to use a formula which takes into account the mean and the standard deviation of the data. And the resulting coefficient can range from -1 to 1, again, where -1 means there is perfect negative correlation, 1 means there is a perfect positive correlation, and 0 means there is no correlation at all. So it is again like having a crystal ball for predicting the future trends. So whether you're crunching the numbers to see how variables relate or comparing rankings to find an agreement or analyzing time series data to predict the future, correlation and its buddies have got your back. So they are like the detectives of the data world, helping you uncover hidden patterns and making a sense of the world that is there around you. So don't worry, we will dive deeper into time series analysis also later on. So stay tuned. Okay. So fitting a straight line in statistical analysis. This serves as a fundamental method to establish a mathematical relationship between two variables. And this process is often used in various fields, especially in industry and business, to analyze data and make predictions based on the relationship between these variables. So at its core, fitting a straight line involves identifying an independent variable and a dependent variable. Now the goal is to find the best fitting line which represents the relationship between these two variables. And this line is determined by minimizing the sum of the squared differences between the observed values of the dependent variable and predicting values based on the independent variable. To achieve this, we estimate the slope and intercept of the line using the least squared criterion. Examining the fitted straight line will involve several steps. Like first we have to identify the independent and the dependent variables. Then we have to make an initial guess regarding the form of the relationship between them, which can be aided by graphical plots or systematic tabulations of the data. Next we will estimate the parameters of the model like the slope and the intercept of the straight line. And following this we will conduct an error analysis to assess how well the model will fit the actual data. This involves statistical tests and determining the standard errors of estimate, which will help in establishing confidence limits for parameter estimates and forecast values. Additionally, an overall percentage variation can be computed to compare the alternative regression models. The least squared criterion plays a crucial role in estimating the model parameters in regression analysis. By minimizing the sum of squares of errors between the observed and the predicted values, this method of least squares criteria plays or you can say this method provides estimates of the quality of fit and the confidence intervals for predicted values. The parameters of the model are estimated by solving the normal equations, which are simultaneous linear equations that are equal in number to the parameters that are to be estimated. So to determine the standard error of estimate of the forecast and estimated parameters, we can follow specific steps. First, we will estimate the model parameters using the least squares criteria. Then, we will quantify the errors of these estimates and establish the confidence intervals for the parameter values. Next, we will quantify the error of the forecast at some point and we will provide confidence intervals for the forecasted values. Additionally, we can test for the significance of regression and obtain an overall measure of the quality of fit. Establishing confidence intervals involves assuming that the variations of the observations about the line are normal, allowing us to assign confidence limits for parameters based on the t-distribution values and standard errors of estimates. By calculating parameter estimates plus or minus the product of the t-distribution value and the standard error of the estimate, we can establish the confidence intervals to make meaningful forecasts from the given data by fitting any function linear in unknown parameters. We will first identify the independent and the dependent variables and then we will make a guess regarding the form of the relationship between them, aided by graphical plots or systematic tabulations. And next, we will estimate the parameters of the model and we will conduct an error analysis to assess the model's fit to the actual data. And finally, we will use the fitted model to make the forecasts, understanding that these forecasts are subject to chance errors due to the assumptions that were made during the parameter estimation. And by following these steps, we can make informed forecasts from the given data by fitting any function linear in unknown parameters. So as promised, time series analysis. I promise you this is the last unit. After that it is done. So time series analysis. This is a cornerstone of short-term forecasting, offering invaluable insights into the underlying patterns of data. By examining the dependence between values in a time series, this analytical approach of time series analysis, this approach facilitates the development of appropriate models to forecast the future trends accurately. Central to this process is the decomposition of a time series into its components. What are they? Trend, seasonality, cycle, and randomness. These are the constituent components of a time series analysis. Once again, trend, seasonality, cycle, and randomness. The trend component reflects the long-term direction of the time series, whether it is ascending or descending or stable over the time. Meanwhile, seasonality captures the periodic fluctuations which recur at regular intervals, such as daily, weekly, or monthly variations. The cycle component accounts for the non-specific fluctuations that occur over more extended time frames, whereas randomness represents unpredictable fluctuations unexplained by other components. Decomposing a time series enables a better understanding of its internal structure, paving the way for a more precise forecasting. Various methods, including moving averages and exponential smoothing, aid in this process by identifying and modeling each component separately. Once established, these components can be combined to generate forecasts which reflect the overall time series. Autocorrelations are another crucial aspect of time series analysis. This measures the correlation between a variable and its past values across different time lags. By analyzing autocorrelation coefficients, patterns like trends, seasonality, and randomness can be discerned. For instance, slowly declining autocorrelations with several significant deviations from zero may indicate a trend, while oscillations around zero with notable deviations may signify seasonality. Moreover, autocorrelations facilitate the estimation of seasonal lengths, aiding in model development and forecasting accuracy. When autocorrelation plots exhibit fluctuations around zero within control limits, it suggests randomness in the data, indicating the absence of underlying patterns. The Box-Jenkins methodology. This has been asked in question papers in term and examinations as a short note question. Box-Jenkins methodology. Box-Jenkins methodology advances the time series analysis, particularly through autoaggressive, that is AR, autoaggressive and moving average models, MA. So autoaggressive models capture the current time series values dependence on past values, whereas the moving averages model reflect the current values dependence on the past errors. For non-stationary processes, the autoregressive, did I say autoaggressive earlier? It is AR is autoregressive, okay. So for non-stationary processes, autoregressive integrated moving average, that is ARIMA, autoregressive integrated moving average model. It is denoted as PDQ is employed, with D representing the degree of difference that is required for being stationary. Box-Jenkins' interactive approach to model building involves multiple stages, including model identification, estimation, diagnostics, and validation. So their contributions have actually revolutionized the time series analysis, offering robust procedures for model selection as well as validation. Choosing a forecast method actually hinges on the problem context and the desired time horizon. Subjective methods like opinion polls or Delphi studies may be appropriate for areas that lack in historical data. So in contrast, quantitative methods such as regression analysis require assumptions about underlying patterns, guiding model selection. Time series analysis emerges as a potent method for short-term forecasting, leveraging historical data to uncover underlying patterns. And once identified, these patterns will inform the various forecasting techniques, allowing for informed decision-making and strategic planning. Ultimately, the choice of forecasting method must align with the problem context and the desired level of accuracy, underscoring the importance of a tailored approach in forecasting endeavors. So with that, as I promised, we have covered all the major aspects of quantitative analysis for managerial applications, that is MMPC 5 of IGNOU's MBA as per the new syllabus. So no matter what your specialization is, make sure that you study this well. because you have another course, as I said earlier, you have another course. It is called as Research Methodology. It is in the 3rd semester. Code is MMPC 15. It is an extension of this MMPC 5, and it is super important when you start your research work also, that is your project. If you have any doubts on any of the concepts that are discussed in the rapid roundup session, please do check the detailed playlist for MMPC 5. I've explained all the concepts to the best of my ability there in detail. So thank you so much for tuning into Anu's Classroom. I hope you have subscribed to the channel and you have enabled the notifications. Your exams might be right around the corner, so all the very best for your term and examinations. And I hope we'll catch up in the next session. Happy learning.